Hello guys and welcome to another video. Today we're going to check out the what is called the momentum integral equation for a zero pressure gradient case. So let's start by writing that up. It's called MIE, which is the momentum integral equation. And in this case, we're going to look at it for a ZPG case. So if you recall from the last video, what is a ZPG? Well, a ZPG is when dp dx is equal to 0. So P1 is equal to P2. So there is no pressure difference driving the flow. So this would effectively just be a flat plate because the flow doesn't see any change in a respective area. So the pressure field is not changing because of that. So the pressure field is constant. And by that is the flow is just developing through this plate. So let's draw this plate case. We'll draw this here. So this is our plate, and then we have our x is equal to 0, which is called the leading edge, LE for short, and then we have x, our horizontal distance, which goes along the plate there. Then we have at our leading edge over here, we have a uniform flow coming in like this, which is called U infinity. That's a constant. And then as the flow evolves over this, the boundary layer will grow. And the boundary layer is basically just you can say it's like it's not an imaginary thing, but it tells you how the velocity field very close to the wall is developing. In a way, it's like a thickness, but it doesn't tell you the shape. It's only a thickness that grows with x. So we can say that, for example, the boundary layer grows like this. It's almost like a function of, it's like x to the power of a half, or the square root of x, which we may be looking a bit more into later. But let's consider that this is the boundary layer thickness, right? And at some point we have a flow profile which looks like this, right? And what is important to say here is that over the boundary layer we have what's called the inviscid zone. There is no viscosity. You could say it as that. So this is like inviscid region. It's far away from the wall, even though the boundary layer itself is very short and thin. So this is what we call the boundary layer, or the boundary layer thickness, delta. Okay, so then we have our free stream here. This is our U infinity. This right here is U is a function of y, because it's a parabolic. It's a parabolic shape, and it evolves as we go with the distance of x. And over the boundary layer we have the free stream. So from here on and out we have U infinity, and from the boundary layer down to the wall we have U of y with the no slip at the bottom. Okay, so I can draw it like this as well. So this is our viscous region below the boundary layer. You can also say that this is the boundary layer. Okay, so the thing is that we are going to derive a set of equation which is going to tell how it's a momentum thickness, how that changes with respect to x, and how that is dependent on the skin friction. So we're going to do this by using a control volume approach. So if we define some set of things before, first, let's say that this height here, we could do it even smaller, we could do it like this. This is some arbitrary height h, okay? We have h, we have delta. H is bigger or equal to delta. And then we have into our paper, we have the b, the distance into our paper, right? Okay, and then we could draw our control volume box around this. So if we draw this, right, this is our control volume, CV or CS, depends on how you look at it. We will consider a control surface because it's what moves in and what moves out, which defines what is happening inside the box, right? And then we also have some forces inside of this control volume. We have shear. So we will have some forces here that is kind of working against our velocity or our profile, right? So we have tau, like that. Okay, so let's consider a control volume approach for this problem. So we say that, well, again, the sum of the forces in the x direction, because we only have flow in the horizontal distance, which is a function of u or u infinity in this case, and we have shear forces acting in the opposite way of our flow or of our x. So we say that the sum of the forces in the x direction should be, again, mass times acceleration. And as we have been through this 2 times already, we say that the acceleration vector a is the material derivative of our velocity field with respect to time, which includes both spatial, if we take the u component, it includes both time and spatial changes. Right? But now the thing is that we know, because we have shear working in this case, that the velocity profile we send in here, which is a uniform flow profile, this is going to change, as we see here. It's going to develop. So, for example, at this distance here, we might have something looking like this, okay? So the velocity profile is changing along x. So we have we have to accommodate for the spatial change. And we still just have a function u of y, but we only have a u component, so v is still 0, which means that this term goes to 0. We also say that we have a steady state case. So everything with d dt moves away. But then this term, we know that our velocity profile is changing with respect to x. So du dx is definitely not 0, and our u is definitely not 0. So this term, all of this is not equal to 0. So then we have to accommodate for that. And by that, we will use something called, it's called the linear momentum equation. So what that basically ends up being is, we have the sum of the forces in the x direction. That is what is going to be, well, it's going to be the sum of surface integral rho u are dotted with the normal vector times, or dA, infinitesimal small area. So what this is, if we express this out, because this is the net change of momentum flux, you could say, this accumulates to a force. We have rho u squared a, if we integrate this. So what this is, in this case, so we say that, well, it's gonna be what we have out, rho. Now I will just write it like a generic way. You are dotted with the normal vector dA minus in rho you are dotted with the normal vector again dA. So it's the net change that accounts for this forces that is happening inside our control volume. And then we have our control volume here, marked in this yellow color. And then what we know is that the normal vector is perpendicular to our control volume. So we have our normal vector on each and every side of our control surface. So now, what we know. Okay, what kind of forces do we have? Well, we have a ZPG case. So the pressure gradient is 0. So that means that the pressure is constant over this part. And that also means that there is going to be no pressure forces acting on our control volume. So that means that pressure forces is 0. And then, well, of course we have shear. In the viscous region, there's going to be shear along the wall. So we have to have something with the shear. Our tau, or our force, drag force, Fd. And that is definitely not equal to 0. That is some positive value. Okay, and then we basically compute this this integral in a way. So again, we had shear, but do you know that the shear is working? The flow is going this way, but the shear is acting in the opposite way, trying to slow the flow down or dissipate some of its momentum, energy, you could say. So that means that, yeah, it's working in the opposite way of our x. So that means that this one, the sum of our external forces acting inside of our CV, that is going to be minus Fd, because it's moving in the opposite direction of what we set as the flow direction from left to right. Now we compute this net flux integral. So minus Fd, our drag force, that should be, if we integrate this, if we take what's coming in first, this is in, right? We have our uniform flow. This u infinity is not a function of any height, it's a constant. So that means that we have, we can drop the integral basically, and we have to dot the dot product of our u infinity with the normal vector. Well, our u infinity goes like this, and our normal vector goes like this. So that means that the dot product between those two are going to be -1. So that means that we are going to have minus rho u infinity squared, and then our dA integrated up is going to be a, which is going to be our height times our depth into the paper. So h times b, okay? And then considering our outlet case, well, the normal vector is pointing this way and our flow is going this way. So they are aligned, they're going the same way, which means that the dot product of u of y and with the normal vector is going to be, well, 1 or +1. Meaning that we're going to have rho, but now u is a function of y. So we cannot simply take this out of the integral and multiply with the area. We have to keep the integral, but we can move rho out because it's a constant. Also, the area is going to be a function of y, but going from 0 to our boundary layer thickness delta. But we also have our b, the distance into the plane. So it's going to be rho b, and then we are integrating from the wall. Y is equal to 0. Y is equal to our boundary layer thickness. Okay, and then we have u of y squared dy. So this, if we integrate this, and we have y, and then we have b, it's going to be an area, rho b times some height times velocity squared. That's a force. All right, so then we have that. So now the next trick in the book is going to be to use continuity. So let's do continuity. I'm just going to check that you can all see. Yep, very nice. So let's use continuity now. We normally do this by saying that, well, nabla dotted with our velocity field is going to be 0. But we do it much more simpler here. We just say that the volumetric flow coming in should be the same as the volumetric flow on the other side, because it's an incompressible flow. So that means that Q, which is our volumetric flow, or we could say that V, our volumetric flow, meters cubed per second, that's our velocity times an area, and that should be constant. That's a mass balance. So if we say this, we say that at point 1, at our leading edge, and at some length where we have u as a function of y, the volumetric flow at this point and this point should be the same. So that means that, well, if we take this example first with u infinity, we say that h b u infinity is going to be the same as, now we have the integral. So we have still b, we have the same boundaries from y is equal to 0 to y is equal to delta, our boundary layer thickness, and then we have u of y dy. And then what we basically is trying to do is that we are trying to get this term, we're trying to express it by continuity. And we see that here we are getting something that is pretty close to this, but we need to find out what is missing from this to this, so we can substitute this into this. So we have hb u infinity. So here we have hb u infinity, but squared times rho. So we need to multiply both sides with rho u infinity. So if we do that, multiply times rho u infinity, we get, it's going to be a lack of space here now, but we have that rho hb u infinity squared is going to be rho b h, our integral from 0 to delta u of y u infinity dy. Yeah, sorry, there's not going to be an h here. It's going to be like that. We multiply with rho u infinity. So now we have the same here as we have here, and we have that we can substitute this into this. So let's do that. So now I'm just gonna need some more space on the blackboard, so give me a second. If we just substitute what we just got into our equation from the linear momentum equation, then what we get is that we have still minus Fd is now equal to minus rho b 0 to delta u of y dy, or sorry, u infinity dy plus our momentum flux from the outlet, you could say, which is going to be rho b 0 to delta u infinity, or u of y, sorry, u of y squared dy. This is going to be a delta, sorry, I am making a lot of mistakes now. And what we can see is that we have the same boundaries for those two integrals, which means that we can put them all together. So if we do this, we get Fd going to be rho b, then we have 0 to delta, we have u of y, then we have u of y minus u infinity dy. So now we just put those integrals into one, correct? And then now what we could do is that we could multiply with minus 1 on both sides. So if we do that, we will get Fd is equal to rho b, still the same boundaries for the integral. Then we have u of y times u infinity minus u of y dy. Okay, and now we are going to bring in something that is called the momentum thickness. And what the momentum thickness basically is it's telling you how much momentum deficit you have in the boundary layer because of the shear, which is kind of removing momentum near the wall. It's eating the momentum up. So if we write down the form for the momentum thickness, it's theta, then we will have, let's see, it is u infinity, it's 0 to delta u of y u infinity 1 minus u of y u infinity dy. So this is something we have to keep in mind, and what the goal is basically here is that we are trying to compare this integral to this integral. And what we are basically missing here is, well, it's a factor of u infinity squared we are missing from, if you compare this one to this one. Okay, fd is rho b theta u infinity squared, because we have rho b here, which comes from here, and then we have theta, which is this one, but we are missing a delta or a u infinity squared from this compared to this. Okay, and now we are getting somewhere. Fd, our drag force, that's some thickness into the plane. Then we have from some distance 0 to a distance x, integrated up our shear function, our shear stress dx, right? So this is a stress, so it's a force per area. Then if we integrate this up, it's gonna be some stress times some unit depth times some length, that's an area. So that is going to be our drag force. And then if we say that df dx, that is just going to be b times our tau, because then we simply remove the integral. So then we are just left with b and tau. And then, well, I think we need some more space now, so I'm gonna clean a bit up. So we have that the derivative of Fd, our drag force with respect to x, is unit depth into the plane times our shear function. So then we can do this and say that dFd dx is equal, we substitute in our Fd from here. We have that d dx, our expression rho b theta u infinity squared. And then we have to see, okay, what is a function of x in this case? Well, our density, that's definitely a constant. This is a constant. B is also a given constant. U infinity is also a constant because, well, it's a uniform. It doesn't change over the length of x. Okay, so let's quickly just go over. Let's go over why I said that u infinity is constant here. Well, one way is to use the Euler inviscid flow. So if we say that Euler, which is inviscid flow, we say that in the x direction, our u component, u du dx is equal to minus 1 over rho dp dx, right? And then if we have our case, our flow over this plate, which is just the same drawing here. Here we have our freestream velocity and the boundary layer that is growing as a function of x. And at some given length we have u of y, because it's fully developed. Along this, which I maybe also forgot to say, is that u is a function of both x and y. That is why in the accelerative term, we said that du dx is not zero, and that because it is under the development. At some given length, it's going to be fully developed, and then it's only a function of y. But that was not the point here. The point is to show that, well, u du dx is minus 1 over rho dp dx, and if we evaluate our u over our boundary layer thickness, so we say that evaluate u when y is bigger than our boundary layer thickness. Well, when u of y is a y value that is bigger than delta, we have that u of y is bigger than delta, that is going to u infinity. Because we know that we have u infinity over the boundary layer, and we have u of y beneath or up to the boundary layer. Remember, this is the inviscid zone over the boundary layer. This is the viscous zone in the boundary layer, okay? So then if we substitute this into here, and we say that, well, in the free stream we have a constant pressure of P infinity. So then what we get, we have that u infinity du infinity dx is minus 1 over rho dp infinity dx. And what did we say in our case here? Well, it's a ZPG case. The ZPG case. So dp dx or dp infinity dx, the change of the pressure gradient is 0. So that means that u infinity du infinity dx is equal to 0. So that also means that, well, our du infinity dx is equal to 0. Here I just divided by u infinity, which is a value, a constant. If we integrate this with respect to x, we get that u infinity is a constant. So it's not a function of x. So now we have just proven that, well, our u infinity for a 0 pressure gradient is actually constant. It's not going to change. So yeah, and we can also show this with Bernoulli, for example. So let's do that. Bernoulli is valid along a streamline. So we say that Bernoulli, that is, from what I know, the simplest form is P over rho plus u squared half is equal to some constant. It's constant along the streamline, okay? And that means that if we differentiate this, we get that dp dx 1 over rho plus our du squared dx 1/2 is equal to 0, because d dx of some constant is 0. So then we move this to the other side and we say that, okay, we have d dx 1 u infinity, or u squared 1/2 is equal to minus 1 over rho dp dx. Okay, then we have that. Here we need to apply the chain rule. So we have that this is going to be, when we derivative this, it's going to be 2u du dx 1/2, because we use the chain rule, the 2 goes down, we have u 2u du dx 1/2. So this one goes against this, is still equal to -1/rho dp dx. And then we see here that over the boundary layer, if our u goes to our u infinity, we end up with the same. And the same being that when we set a ZPG, the dp dx is going to be 0. Well, u du dx is going to be 0. And we integrate this again as we did with the Euler. It's still going to prove that, well, for ZPG, the u infinity is a constant. That is the main point from this. So now we're just proven that both with the Euler inviscid equation and with Bernoulli, if we differentiate Bernoulli, we will end up with the same if we use that over the boundary layer where the velocity is the freestream velocity u infinity. I hope that makes sense. So the only thing we have left is that this is a function of x, our momentum thickness. Then if we then take out rho b u infinity squared out of the derivative, we will get that rho b u infinity squared times d theta dx is equal to our b times the shear stress. And then we could simply cross out these two terms, the b, and then we are left with rho u infinity squared d theta dx is equal to tau. Okay. And then we have something which is called dimensionless skin friction coefficient, our CF. So CF, that's tau divided by 1/2 rho u infinity squared. So if we solve this for tau, and then we put this into here, we will see that we are too short, you could say. So what this all gives to, if we substitute tau into here, and then we have these two terms already here, we see that d tau dx is equal to CF, our local skin friction, over 2. And that is our momentum integral equation for a zero pressure gradient. Right? So then we could see that, okay, this one, the theta, we define that as this function, and that is a function of our u of y, our viscous flow beneath the boundary layer. So given this, we can calculate our theta, momentum thickness, and then if we derivative this, we will get the skin friction, the local skin friction, and then we could go from that to our combined or total shear. So this is a nice way to basically find a relationship between our velocity profile, u of y, and the skin friction coefficient. And what we see here is that we have a uniform flow here, and as it goes, it will develop like this, right? So here we say that, okay, well here we have no shear. At the leading edge we have no shear. At some given x value, we could say that this is x1. We have a gradient, velocity gradient. We remember that tau is proportional to du dy. So this, if we call this tau 1 at this given x is equal to 1 position, then we have at some other position x is equal to 2. Well, we have an even steeper gradient like that. So then we have tau 2. And then here we say that the gradient is even steeper at this x is equal to 3 location. So we see that the shear is increasing with our flow moving in the x direction. So it's basically taking away momentum from, or you could say energy from our flow. And this is the whole point of this equation. That is telling you the relationship between our momentum thickness that is changing with respect to x and our shear, our local shear at a given point. So, yeah, and one thing you can also do is that you can, this is a separatable ODE, first order, you can separate this and you could say, you can basically find an expression for the total shear. If you multiply with dx on both sides and you integrate with respect to dx, you will have some difference in theta is equal to, well, some function of the shear, total shear, or the shear over that span of x. So, yeah, I hope you guys enjoy this, and I will see you guys in the next video. Thank you.